Hello everyone. This lecture is exclusively recorded for second year BSc student of BK Birla College, Kalyan. In this lecture, we will study the Eulers Theorem for the two variable and the problem based on the Eulers Theorem. So let me state what is Eulers Theorem. For two variables. The statement is as follows: if f of x comma y be a homogeneous function of degree m n in two variable x comma y possessing first order partial derivatives, then x times dou f by dou x plus y times dou f by dou y is equal to n times f of x comma y. Right? So proof is simple, but to prove this theorem, one should know what is homogeneous function. So let me define what is homogeneous function quickly. So, definition of homogeneous function. So if f is a function from R2 to R, so in general now I'm defining, let me define this from Rn to R be a scalar valued function then f is said to be homogeneous function of degree n if, note that this n belongs to rational number here, if and only if f of x1 comma x2 comma xn, so I should say t times xn, t times x2, t times xn is equal to t raised to n. So let me take here m is same as f of x1 x2 dot 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 xm, right? So this equation should satisfy. A quick example, if I take f of x comma y as x square plus y square, then you could see that f of tx comma ty is same as t square times x square plus y square, which is same as t square times f of x comma y. So this is homogeneous function with degree 2. I can take one more example. F of x comma y is equal to x upon y provided y is not equal to 0. So let's find out whether it is homogeneous or not. F of tx comma ty is same as tx upon ty, which is x upon y, and which can be viewed as follows: t raised to 0 x by y, which is t raised to 0 f of x comma y. So you can see that f of tx comma ty is same as t raised to 0 f of tx comma y. So it is a homogeneous function of degree 0. With degree 0. We can have one more example. F of x comma y is equal to x square plus y. So you could see that f of tx comma ty, here it is t square x plus ty, and you, even if you take t common, then it will be tx square plus y. So which cannot be equal to t raised to n f of x comma y. So it is not homogeneous function. So f is not homogeneous function. Okay. So since we have done what is homogeneous function, so we can now define our, we can prove the Euler's theorems, right? This proof we can do. So let's go for the proof. So, proof of Euler's theorem. Right. So it's given fact f is homogeneous function with degree n. It's so f of tx comma ty is t raised to n f of x comma y, that we know. Now what I will do is as follows. So what I is as follows. So uh, let me take let u equal to tx and v is equal to ty. So how the function will look? It will look as follows: t of u comma v is equal to t raised to n f of x comma y. Right. So correct. So now what I'll do, I'll differentiate this expression by t. Now you try to understand that my function f in this case depends on u and v again depends on t. I hope it is okay. Uh, no, yeah, f depends on u and uv again depends on, uh, can you say t? Yeah. So what I'll do, I'll differentiate this equation with respect to t. So if I want to differentiate this with respect to t, then how will I do this? So d by dt of f of u comma v is equal to d by dt of t raised to n f of x comma y. So this derivative is dou f by dou u and dou u by dou t. So you should say here u depends on t as well as x. Similarly, v depends on t as well as x, because here it is is tx and v is ty. Yeah. So u is a function of t comma x and v is a function of t comma y. So plus similarly dou f upon dou v into dou v by dou t is equal to, Here, how will I take the derivatives? Here I will, this is f of x comma y. It is independent of t, so that will come outside. So only t raised to n ka derivatives, n t raised to n minus 1. So f of x comma y will remain as it is. Right. Well, so what is dou u by dou t? From this you can easily find out dou u by dou t is equal to x. Dou u by dou t is x, and dou v by dou t is again y. So that I am going to use here. So this will be replaced by x and this will be replaced by y. So what it will be? X times dou u by dou f by dou u plus y times dou f by dou v, and here n times t raised to n minus 1 f of x comma y. Now what I'll do, let's call this as star. So put or take star is take t is equal to 1, take small t is equal to 1, then star becomes, how it will be, x dou f by dou u plus y dou f by dou v is equal to, here n will remain as it is, t will be t 1 to the power n minus 1 will remain as it is, x comma y. Now note that if I take t is equal to 1, then we know that somewhere we have written u is equal to tx. So your u is equal to x and v is equal to y in that case. So since note that u is equal to tx, so in that case you will have u is equal to x and v is equal to ty. So in that case here v is equal to x. So taking partial derivative of f with respect to u is equivalent to saying that taking partial derivative with respect to x and taking partial derivative with respect to v is equivalent to saying that it is y, I'm sorry, taking partial derivative with respect to y only. So this will be x times dou f by, instead of u I will say x because your u is equal to x. Similarly plus dou f by dou y, here it will y will come, and here n times f of x comma y. So this completes the proof of Euler's theorem. One can easily prove in a higher dimension. So for three variables, it is x dou f by dou x plus y dou f by dou y plus z dou f by dou z is equal to n times f of x comma y comma z. One can generalize, so this can be proved. This is a very good homework you can try at home. So in general, for n variable, one can prove in the following way: x1 times dou f upon dou x1 plus x2 times dou f upon dou x2 plus dot 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 xn times dou f upon dou xn is equal to n times f of x1 x2 dot 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 xn. So this is generalized, and the Euler's theorem is applicable only if your function is harmonic. If your function is not harmonic, you cannot apply the Euler's theorem. Let us have a quick example of Euler's theorem. Examples. Uh, if f of x comma y is equal to x raised to 4 y square sine inverse of y upon x, find x dou f by dou x plus y dou f by dou y. Now you could see that using Euler's theorem this will be very easy if I know my function is homogeneous or not. So I just need to check whether function is homogeneous or not. So solution: my f of x comma y is equal to x raised to 4 y square sine inverse y upon x. So what is f of tx ty? You could see that it is t raised to 6 x raised to 4 y square sine inverse of y upon x. So tx upon ty, but tt will get cancelled, so it is sine inverse y by x, and this is same as t raised to 6 f of x comma y. So f of tx comma ty is same as t raised to 6 f of x comma y, so it is a homogeneous function. So f is homogeneous function with degree 6. So by Eulers theorem, x dou f by dou x plus y dou f by dou y is equal to 6 times x raised to 4 y square sine inverse of y upon x. You can see how beautiful the theorem is. You need not have to find out the partial derivative. You can straight away evaluate the answer. So this is how the advantages of your Eulers theorem. Then another example, second example, f of x comma y comma z is equal to x plus y plus z upon root x plus root y plus root z. Question is find x dou f by dou x plus y dou f by dou y plus z dou f by dou z. Now again this is a left hand side of Euler's theorem. I just need to check whether f is homogeneous or not. So f of tx comma ty comma tz is equal to, you can say tx plus ty plus tz, and here it is root t root x plus root t root y plus root t root z. T will come out from denominator, root t will come out, so it is t upon root t x plus y plus z upon root x plus root y plus root z, and this is t raised to half f of x comma y comma z, because this is my f of x comma y. So I got f of tx comma ty comma tz as t raised to half x comma y comma z. So f is homogeneous function with degree half, right? So by Euler's theorem, you can say that x dou f by dou x plus y dou f by dou z plus z dou f by dou z is equal to half times, it is n times f of x comma y. So x plus y plus z upon root x plus root y plus root z. You can see that beautifully it gives a partial differential equation without much effects. So there are many such examples wherein you can easily find out the integral answers, partial derivative answer. So even I can give you one small homework which you can try at home. So prove that x dou f by dou x plus y dou f by dou y is equal to 0 if f of x comma y comma z, f of x comma y is equal to e raised to x by y sine x upon y plus e raised to y upon x cos x upon y. That can be done very easily. Here you can see that the degree is basically 0. So if the degree is 0, so n times f is equal to 0. So that one can check out. So that's it for the today's. Thank you so much for joining the lecture. Have a nice day.